Okay, so within this video, I'm going to be showing you exactly how you can use the Design Explorer tool within the new HyperWorks 2021. Now, by the end of this video, hopefully you'll also be in a position where you can take this bike frame after you've conducted a design exploration on it, a DOE. You can start looking at whether if your input responses have a linear effect to your output responses, so you can see whether if your displacements are positively or negatively correlating towards your input variables, and if they are, then how big is the effect on all of the different responses that you have. So we're going to go through and show you exactly how it is you can post-process this. We're going to show you how you can take the data that you do have, that you've accumulated from all your different runs, where you can conduct a fit, and you can see whether if you were to interpolate it for a value which you didn't solve for, how accurate these output responses can be estimated for you. Obviously you can also put down a different scatter plot. We can go back to our different runs that we've conducted, so altogether we have 40 sets of data that we can look at, and how you can simply right click, load some results, and you can see exactly within this run where we've got all of these different thicknesses that we've input into this bike frame. We can see exactly how it's performing, and you'll see that the design exploration tool will automatically extract the output responses that you care about. So without further ado, let's actually start looking at conducting this ourselves. Okay, so let's start a new session of HyperWorks, and what I'm going to do is bring in my original bike frame model with it too. So here's a new session of HyperWorks. You can see that we're currently in the geometry toolbar, we're working in the model browser, and this window here would be where we do all of our modeling entities. So that would be the GUI where we interact with the model. Now if I were to bring up folder, here I have my original model. I can simply drag and drop it in to open it up, and you can see I have a bike frame here. We have a few components of different tubes. You can see it's loaded in the one load case called crank, and with this we can see exactly where all of our constraints are attached to our model, and we can also see that we have a force acting at the center of this crank. So what we're going to do is first just look at the model that we're dealing with. We can see that we have quite a few different property cards, so each of them have a different thickness. Well, currently they're all the same at 2 mil. And what we can do is, just to add to our design exploration a bit, what I'm going to do is morph this location of this part and see if the location of this part will have any effect on our final results. So if you head into the morph ribbon and click on free morph, we're going to move faces, and I'm going to move this part here. And what we're going to do is just click on this plane. Let's say we add 50 in the x-axis, and let's extend the height of it in Z by 100. And if we're okay with that, simply right click and swipe left to exit out of the tool, and you can see it's now morphed itself properly. So if we go into the shapes, there's a plus icon. What I'm going to do is click on the plus, and I'm going to add it as a shape. So how we go about this is the fact that I can rename this and call it height, and what this does is that if I undo all of my morphing, so I'm back to the nominal position that I was in previously, I can then preview all of the other sort of morphing variations that I have within this model. So if I were to click on preview, you can see exactly how I'd move it by and how the rest of my components would adjust and morph itself to the new design. I can do the same with this taller morph as well. It just extends the height of this blue tube, and the same with the crank radius. I can extend this one, and you can see the moment we preview it, it increases the size of that hole. And with the morph volumes, you can see that they're represented with different vectors. So all these node perturbations will change the position of those nodes. So now that we have a few variations in our design, what we want to do is actually see how changing that position of this part and changing the size of this radius, and maybe even changing some thicknesses in the bike frame, will affect our results. So to start with, what we need to do is actually understand how it's currently performing. I ran an analysis on this bike frame already, so we know that if I wanted to look at the stresses in our subcase crank, what we can do is look at where our maximum stresses occur, and we can see they're mostly around in this component here, as well as this one there. If we want to then check for displacements, we can see that it's fairly minimal, around 0.08 being in this component, but then if I were to look at all of them, and it's still roughly, it moves the most at the top of this bike frame. So now that we have a good understanding of how our bike's performing, we can obviously conduct a DOE to understand how it is we want to improve its performance. So back to where we were, in this case, we're going to head into the Design Explorer toolbar. Within the Design Explorer toolbar, you'll see that we have the ribbon to access how it is that we can conduct a DOE. We'll click on this plus sign, and within this plus sign here, we can then add a DOE. And with this newly added DOE, we can also specify exactly where it is we want to save it. So one of the things that I just wanted to make you aware of is that when you do conduct a DOE, just make sure you have enough hard disk space, some hardware space to put it all in. So in my delete me folder, what I'm going to do is create a new folder, and I'm going to name this demo. I want to save all of my results into this demo folder, and you'll see that the location is all located here for me. Once that's done, if you were to click on this compass, because we want to find the direction in our designs, you can see that this brings up our Design Explorer browser. And it's great, because then from this point here, we can go through and click through exactly what inputs we want to put in, and what outputs we want to get out. So let's start with looking at gauge. Gauge basically looks at the thicknesses of your properties. I want to specify a DOE to explore the thickness of this part, this part, this part, this part, and let's do this one down here as well. We can give it a percentage by how much it can increase and decrease by. So let's say I want to increase it by 100, and we can also decrease it by 50%. So it can either double itself in thickness, or it can reduce itself down to being half its thickness. And just so you know, you have other sort of settings that you can implement. So you could have it so that they're discrete values, if you want to increase or decrease in that format, or you can increase it or decrease it in the form of a percentage. I'll just keep mine to percentage, and the moment you click create, you'll see all of your input variables are created for you. Now at this point, I can then go through and specify that I also want to incorporate my morphing techniques into this. I only want to focus on my crank radius and the height of my bike. Click OK, and they're also there for you. But just so you know, you can look at the dimensioning of your different beams. You can also look at changing the material card assigned to your different properties to see whether if maybe, aluminium or steel would be more appropriate to the design that you have. Now at this point, you can see that if I were to click on any of these tiny tables, I can look at the review inputs. You can see that we're playing around with the thicknesses of our components, and we have two morph volumes. In the details, this is where you might want to change some specifications. So where it's 0, it might be something that you can change. So let's just say for now that I'm willing to let these thicknesses go down to 0.5. And what I can do is just assign 0.5 to all of them, because obviously if our property thickness goes down to 0, we're going to get errors, as with 0 property thickness means 0 stiffness, 0 mass, so it's not going to work. But we can move it down to 0.5 for now. And what's nice is that within the same input table, if I were to click preview, so if I didn't know what the seat tube thickness was, I can click on preview. It will show you in isolation that we can look at this, and with the preview slider here you can see what it looks like when it's at its absolute thinnest, and what it looks like when it's at its absolute thickest as well. So this preview shows you exactly what it is that it will be varying. I can also click on height, and it shows you that it varies the positioning of these three components. Same when I do it with the crank radius as well. You can also create links between your different thicknesses, so say if you know that certain tubes have to be the same thickness as another one, you can always link them up, so that if one of them's one thickness, the other one follows with it. So that's one way you can review your inputs. Now on the next part, what we can do is start specifying, the responses, the outputs that we care about at the end of our analysis. If I were to click on that table, you can see we currently don't have any. So what I'm going to do is just click on this mass property, and instead of looking at mass, I want to look at volume, the total volume of my design. And the moment you accept it, it's there listed in your browser again. I can look at the displacement of this node, and I'll tick for it. Same again, I can do the same with the stresses in my components. I care about the stress in this component as well as this component, and then you can specify a load step that you want to get the results from. And once that's all done, we can click on accepting it, and you can always review these in the entity editor, so you can look at volume, displacement. Again, we can assign a load step to this one. We can specify the magnitude and whether if we want it to be the absolute maximum or if you want it to be the XYZ component. And same with our stresses. You can specify, obviously we've already specified the two properties, and we can get the response component out of it too. Now once we've specified all of our output responses that we care about, we can tell the solver algorithm to solve for our different designs. At this point, if we were to click on the play button by the evaluate, we can see that we can specify our DOE type. So if you're looking at a full factorial, that's looking at your whole design space. So this is a screening algorithm, whereas MELS is a space filling algorithm. So if you just wanted to understand a good sample size of what your designs look like throughout its variety, then you can use MELS. I would recommend that you go and do a bit more research into the algorithm types so you know exactly which one you want to look for. Now I just want to get a good sort of sample size of my space filling algorithms. So I'm going to select MELS in this instance. And based upon the number of inputs you have and the outputs you want, it does go through an equation to specify the minimum number of runs that you should go for to get good results. So let's just leave it at 40. We can have it so that it can solve 5 jobs at once. There isn't a limitation on this, just make sure you don't set your laptop on fire. I can choose my OptiStruct solver in this case, and a solver argument would just be the arguments that you want to use with your solver. So in this instance I'm going to put -nt space 6 because I want it to use all 6 cores of my computer to solve. Now at this point what I'm going to do is just click export, and I will click run. From here you'll see that we have an evaluation status bar or table, and through here it will show you exactly when something's processing, when it's pending, and once it's gone through it will solve itself, and once it's done and extracted everything that you needed, then the status will also turn green. So let me try and enlarge this box and expand it further down. And what's also really nice is that without you having to change your solver deck yourself or vary your model parameters and go through and then extract everything, instead of that long, lengthy manual process, HyperWorks here will do it all for you. And where we saved our folders, where we saved our file, so remember that we mentioned the demo folder earlier on where I saved this DOE into. In the demo folder, all of the variations that it's creating, you'll see that it's put them into new folders for you, and it'll also have written out the solver deck that you'll be needing. So in Model 1, we can see it's written out the solver deck, it's got the animation file, and HyperWorks is going through to extract those values for you. So you don't even need to, after understanding your data, you don't even need to go and make your model again with the right variables. Your models would have been made for you, and all you need to do is head into the right folder to use the model and use the design that you need. So let's just let this solve in the background, and once everything's done you'll see everything will be green. Okay, so once everything's solved, you see everything's green, what we can do is close that table and click on the triple I icon. Once we click on that, this will load up all of your different results from that design exploration. You can see the different values of your inputs, so all of your thicknesses, from the seat tube thickness to the top tube thickness, and you can see the respective outputs as well that you've selected for. So you can look at the volume, the displacement, the stresses associated to each run. Now we can also start looking at the linear effects as well between your data. So to actually really understand your data, you can see just how your inputs would affect your outputs. You can look at the relationships between them, whether if they're positively correlated or negatively correlated. You can see at this point, say if we were to increase the thicknesses of your different tubes, this in turn would obviously increase your volume. And from there you can see it with the positive contour and the colouring of your plots too. Same again, we can look at stresses. So if we were to increase the thicknesses of your different parts, you can see there's a negative linear effect on your output stress results. So you can see that the thicker it is, the lower your stress will be. Now at this point in time, obviously you can look at a different response, you can look at displacements. We've already covered our data and linear effects, but you can also plot for the trade-offs as well as the scatter plots as well within your results. So if we were to click on the trade-off button, what this is doing in the background is that it's applying a surface fit to all of the data that you have. So where you see these different sliders, it will show you where you could slide to any different values, ones that you might not have actually solved for. So you can slide it to any values, and through the given data that you already have solved for, it will look at interpolating the results between them to get you the responses, so you don't need to go through and run another analysis solve all over again. So where we can put the different slider at different values, this in turn calculates your response values, and obviously you get the R² value at the end to show you how accurate those values are. And if we go back to our full set of data, we can look for where we have the result with the highest volume, and if you were to right click on it, you can also load the results. This in turn will launch up Hyperview in the same session, and it will show you a contour display of the different results you have from the different solves that you've run for. So from here you can look at the displacements, the displacement contour, but you can also then change this displacement contour to looking at a stress contour instead. And where you can see the values of your different contours, and if we were to play our animation, you see that it doesn't really deform too much currently. So what we can do is head into a specific tool called Deformed, and through here we can specify a graphics, deformation contours, and magnification. So we can magnify it by, let's say, 100 as a scale factor, just so you can see exactly where our frame will bulge throughout the analysis. And you can see how it's buckling to one side, and there where your maximum stresses are. Now from this point, what we can also do is actually visualize our plots. So we're going to divide off our page into 3 separate windows, and in this third window what we're going to do is launch up Hypergraph instead. And in Hypergraph you can plot your chart data in a lot of different ways. Today we'll be using the line chart, because what we want to do is look at the scatter plot, and along the x-axis we can specify exactly what it is we want to look at. So we can look at the down tube thickness versus our stress values, and you can see exactly the pattern between the different thicknesses you assign your part to be and the stress values you get from it. We can look to plot something else at this point, so we can look at, same again, the down tube thickness, but this time against the volume, and where from these scatter plots you can see if there's a positive correlation between your data as well, where the thicker it is, the higher the volume. Now if we're just going back to looking at all of our different results, we've conducted a DOE, but what we can do is duplicate this DOE that we have and actually turn it into an optimization instead. So the difference between a DOE and an optimization is that with an optimization, you're giving it a direction to how it can give you an optimal design based upon what you're looking for. So same again, in your Design Explorer browser, you can find the optimization run that you want. We will then assign some objectives, so we can give it a response of the volume, where we want to minimize this volume, but then we want to minimize this volume with respect to some constraints. So what I can do is create a constraint against our stresses, where we can give it an upper and lower yield value. And this yield value can be, let's say, 250 in this instance. And if we click OK, you'll now see we have two new points here. So we want to minimize the volume, but ensuring that our stresses don't exceed over 250 megapascals. And at this point, same again, where you can click to solve. Number of runs can be 50. We can give it multi-execution. Now I just want to solve this very quickly. So let's say that I only want it to run for 10 runs, and I want it to give me the best design out of those 10 runs. You know, which design gives me my objectives and constraints. Again, I'll specify it to solve with 6 cores. And I'll let this run in the background very quickly. Okay, now once this is all done, you'll see everything's in green again. Same button. We'll just click on the I values, and the difference between an optimization and a design exploration that we just conducted is the fact that what we're doing is giving the solver a direction as to how it should vary your different input variables to achieve the optimal targets that you wanted. So you'll see anything in green tells us that's our best design that we've got, and it'll tell you the best iteration, the condition, whether if it's feasible. And because we know that this is feasible, it's optimal, it will show you that this is our best design out of all of the 10 runs that we've done. Same again, you can right click to load your results and it'll bring it up in a new window for you. You have a few more other graphs that you can look at, so whether if you want to look at your evaluation plot, your iteration plots, and you can also then again look at a scatter plot between your data between them. And this is Design Explorer in a nutshell. Thank you very much for listening to this demo.